More on the dynamics of circular motion. A 1,500 kilogram car is traveling on a level road where the coefficient of static friction is 0.45. What is the maximum speed in meters per second that the car can safely navigate a turn of radius 20 meters? Alright, so let's draw our free body diagram. We're going to have, of course, the weight pulling down and the normal pulling up, pushing up. We need to be careful here. First of all, let's be a little more careful. They should be they should be the same size. So maybe more like that. Second, we've got to figure out like where is the force going. So if we are looking from above, or looking from the side, then the force of friction is going to be horizontal. And I'm going to choose that we're taking the moment where this is coming out of the page, but towards us. So if we're looking at it sort of, it's doing a circle and it's coming out like this, out of the page. Which is tricky because we don't have any symbolism to be able to draw that. So the convention in physics is that out of the page is a dot protected by a circle. And then at this moment, then the centripetal force would be towards the center, and therefore the frictional force must also be towards the center. And then we can say, well, the frictional force will equal its maximum, which is mu times Fn. We can do from free body diagram stuff. The frictional force is going to be equal to the mass times the acceleration radially. And the normal force minus the weight is going to equal the mass times the vertical acceleration, but that's 0. This tells us that the normal force equals the weight equals m times g. And the one above here then tells us that our frictional force is mu s times m times g. Now our next thing though is that we know that Fs has to be mv squared over r. And so we can turn this around to say that v squared has to be FSR, or mu FSR over m, mu mgr over m, or just mu gr. The actual calculation says that we get a speed of just about 9.39 meters per second. Any faster, and the friction will not be able to be large enough to give us the correct acceleration, so the car will spin out some and will not go in a circle. By the way, why do we pick a dot as a circle, meaning out of the page? Well, imagine we fired a vector, which remember looks like an arrow, and it was coming out of the page. The first thing we would see would be the point. So that's what we're saying. What if we fired the vector into the page? So we want the complement. Well, then we would see this, the so-called fletching, the things on the back of an arrow that are usually often done as feathers. They give stability. And as the arrow passed into the page, the last thing we'd see would be the fletching, which would look like an X. So into the page is drawn as an X protected by a circle. All right, a skateboarder is skating over a circular bump at the instant shown to the top of the bump and moving with a speed of 5 meters per second. Is the normal force on the skateboarder by the bump greater than or less than or equal to the weight of the skateboarder? Going to draw a free body diagram. For the moment, I'm going to draw them as equal, but I don't mean that yet. Instead, I'm going to say, well, as she goes over the bump, there is a circular motion towards, which means an acceleration towards the center. So the net acceleration, the acceleration is down, which means that in fact, the gravitational force should have been the longer vector, so that the net force points down, which means that the normal force must be less than the gravitational force. Alice swings a ball of mass half a kilogram in its vertical circle using a string of length 0.25 meters. At the top of the arc, the ball is moving at 3.0 meters per second. What is the tension in the string in newtons? There's a little picture here for us. We draw a free body diagram. There is a weight pulling down. There's also a tension pulling down and acceleration towards the center of the circle, which is also down. Step 3 in our recipe from constituent equations. From our circular motion, we have the acceleration is v squared over r, which turns out to be 36 meters per second squared. From the free body diagram, we get that the net force in the y is g pointing downward and ft pointing downward. Here I've taken that downward is a negative direction, so they both get negatives. From the second law, we know that that the net force is ma, but a is also pointing downward. Notice that there's no horizontal force pulling the ball to the right. The inertia is enough to carry it to the right. We don't need to be pulling it to the right. The force is pulling down, redirect that velocity, which is what we need. So we say that F net equals F net, or these guys equal this. We notice the minus sign cancels out the way we would have expected. We could have taken the downward to be positive, and then we would never had those minus signs. Doesn't matter. And then we can solve for the tension. And the tension would be MAC minus FG, and when you grind out all the numbers, it's about 13 newtons. All right, on a level road, the highest safe turning speed is controlled by the coefficient of static friction. Problem is that that's unpredictable and uncontrollable. The static frictional coefficient can change. It might rain. There might be leaves. There might be snow. One way you can compensate is to tilt the road for the span of the turn. That mixes the normal force into the centripetal direction, so that even if mu were 0, the car could make the turn. This process is called banking the road. It's a little bit complicated. So the top view is we have the car doing something like this. And so there's a velocity this way, and we have the centripetal acceleration has to point this way. But if we look from behind the car, so now the car is going into the page, that's the velocity. Then the centripetal acceleration is here. Oops. Because it points towards the center of the circle. And then we can say we have a weight and a normal, but the normal is offset, of course. And so we have this axis, and even if there's no friction, so we're talking about frictionless word, then we can still get some part pointing this way. This doesn't actually look like it's correctly drawn, but oh well. The net force can point to the center. Now it's just some Grungy algebra. Fn sine theta, which is the part of it which is pointing towards, all right, so we have Fn, and we want this part of it, and we have that angle. So this is Fn sine theta, because this is Fn. That has to give me mv squared over r, because it has to provide the centripetal acceleration. Whereas Fn cos theta has to balance gravity. We can combine those over to here, and then we can do a cute trick by isolating the Fn stuff. If we divide this equation by this equation, we have, of course, that Fn over Fn will cancel out, and m over m will cancel out. And we're left with tangent theta equals v squared over gr. So that relation has to hold for the car to make the circle, which tells us the velocity has to be square root of gr tan theta. You might have noticed how often this square root gr is coming up, because it's the only thing dimensionally that will give us a velocity. So there can be dimensionless things attached to it, but there's got to be something like that. So as an example, a given interstate exit is 95 meters in radius. If the exit has to be safe for cars at 20.1 meters per second under all conditions, what is the required banking angle? And we go back to here and we say, well, the tangent of the angle is v squared over gr. So 20.1 meters per second quantity squared over 9.8 meters per second square times 95 meters. This is 0.434. So theta would be the inverse tangent of 0.434, which turns out to be 23.5 degrees. That's probably actually too much, probably more like 24. Too many sig figs there, but 24 degrees, which is a pretty heavy but not crazy angle to tilt the road.